So here we are. Thank you so much. On behalf of Xylem, I extend hearty welcome to all the participants joining this webinar. So this webinar is on UV disinfection and ozone oxidation systems for water and wastewater treatment. You can log in for further details on our website given over here, and for any queries, sales related, you can mail us at indiasales@xyleminc.com. So few updates for the participants. So the duration for this webinar will be from 2 p.m. to 3:30 p.m. That's the Indian time. And we request you to place any questions in the Q&A tab that you can see at the bottom of the screen. We'll try our best to answer all the questions during our session. And we request you to please keep your questions quite precise and quite related to the content of the webinar. For any sort of technical questions for panelists related to this webinar, please place it in Q&A tab. For any other suggestions or any comments on the audiovisual connectivity or any related to that, please place them in the chat section. Otherwise, please don't use the chat section. We will send you a survey link post this session and to submit your feedback. So we'll appreciate your help with the same. I'll just brief you about the speaker's profile. So we have quite
me clearly and well. Xylem, with the Radico brand, is now for over 40 years active in the water and wastewater treatment, globally serving municipal and industrial customers. Radico's experience is based on a strong portfolio and over 200,000 ozone and UV installations worldwide. And that is ranging from treatment of half a cubic meter to over 90,000 cubic meters per hour. Our headquarters for the Radico product is located in Germany, very centrally, and it's on the key logistic routes to reach all our customers. The work is based on 300 employees who are building, researching, and designing the Radico products. I'd like to take you on a small, short company tour. Here you see our production facilities in Germany that are making all our UV and ozone products. And that is ozone systems, what you see here, closed vessel UV systems. However, we are not only operating from Germany, we also have localized production sites all over the world. And that is an ozone system production facility in China. We are building open channel UV systems in India, and we have an assembly site in the US for ozone products. If we look at India, the Radico brand is very well represented within the Indian Xylem infrastructure, and that is going not only geographically in many locations, but also from the functions of support, sales, and design, and even R&D of our products is taking place in India. And as seen on the previous slide, in, I hope I pronounced it correctly, Bangalore, we have the UV production site. And with this, I like now to hand over to my colleague Per Krüger for going through the UV disinfection products.
Thank you, Tim, for handing over. This is Per Krüger speaking, and I would also like to welcome all of you. It's really an honor to present to such a big audience, and I hope that you can hear me well and that you're all healthy and well. In the next 30 minutes, we will take a look at UV disinfection, understand first what disinfection means, how UV radiation can be used for disinfecting pathogens, how UV is produced, how a UV system can look like, how they are applied, and with our portfolio, and rounding out with look at the overall benefits of UV disinfection. Now, what is disinfection? There may be different understandings, especially when it comes to understanding disinfection versus sterilization. Sterilization means a complete, full, 100% absence of any microorganism. This is not what disinfection means. Disinfection means the reduction of harmful, means pathogenic, disease-causing microorganisms down to a concentration which is not harmful anymore. And this reduction in general can be achieved by killing, by removing, or by inactivation. And disinfection in general applies to different types of pathogens. Those can be bacteria, can be viruses, coronavirus being one of those, being very in the public perception today, of course, and also parasites like Cryptosporidium, for example. Disinfection methods can generally be divided in chemical disinfection. Classic disinfectant here is chlorine, but also alcohols are used for hand disinfection or surface disinfection, for example, hydrogen peroxide, and also ozone, which will be subject to presentation later on, has a disinfection effect. Physical disinfection means would be heat, filtration, and radiation, for example, UV light. All those treatment disinfection steps have their strengths and weaknesses. One aspect to be kept in mind is that organisms have different sensitivities and react in different ways to disinfection processes. There are certain pathogens like parasites that are not that are pretty resistant against chlorination, and this is where other treatment technologies like UV have a specific strength. But we'll come back to that aspect later on. So what is UV radiation? UV radiation in general is part of the electromagnetic spectrum, and it's very close to the visible light from 400 nanometers to 780 nanometers, which you see in the center of the colored bar. If we walk away from the blue light down to shorter wavelengths, we leave the range of the electromagnetic spectrum that we can see with our human eyes and go into the ultraviolet range from 400 nanometers down to 100 nanometers. And this wavelength range, the UV wavelength range, can be divided into three areas, which is UVA, which causes sunburn, UVB, also causing sunburn, but also having also certain germicidal effect, and the UVC range between 200 and 280 nanometers, which is responsible and can be well used for disinfecting pathogenic organisms. UV light is part of the natural sunlight, but only at a very, very low percentage, and most of the light that is considered sunlight is in the visible range. Next slide, please. So how does UV work? The UV light is absorbed by the microorganism. It penetrates the cell wall of a bacteria, for example, represented in the upper right corner of that slide, and gets into the center of the cell where the DNA is residing, and there then the UVC light is destroying the DNA acid. That means without a well-functioning DNA, the organism is not able to replicate, to reproduce itself anymore, and by that it's activated. Having, for example, one pathogenic organism inside of our body is not critical. what makes it critical is the fast reproduction and the fast growth taking over control of the body. With destroying the DNA through UV light, this is inhibited. So inactivating the pathogens by UVC light means disinfection. How is UV light generated? This works through specific UV lamps that contain a very little amount of mercury. This mercury is activated in an electrical field. By that, the mercury atoms are activated, are taken to a higher energy level, which is not stable, and the mercury would like to return to an stable, lower energy level, so it releases that surplus of energy, and this surplus of energy is UVC light that we just looked at before, having that germicidal effect in activating bacteria. In principle, you can imagine this UV light to look like a fluorescent bulb, which is or has been used for office lighting, for example, but the UV light used for disinfection, those lamps are very different in design, in technology, and in specific features to reach a very high efficiency level when it comes to a disinfection effect. The lamps that we just looked at are then installed in UV systems so that the water that contains the pathogenic organisms is brought in contact with the UV light in a very efficient way. You see here an example of a closed reactor which becomes part of a pipeline in a drinking water works, for example, or in a wastewater system. So the water runs through that reactor continuously from the right side and then leaving on the left-hand side through the top flange. The lamps are installed inside of the reactor, surrounded and protected by quartz leaves so that the water do not get in contact with the electrically charged lamps. The UVC light is continuously monitored by a UV sensor, which makes sure that the quantity of the UVC light applied is always in compliance with the disinfection requirements according to the design of the system. The system then also has to be powered. The lamp has to be controlled and managed properly when it comes to voltage and current, which is assured by electronic boards called ballasts, which then are housed in an electrical cabinet equipped with a controller. So these are standalone systems that just have to be connected to suitable power supply, and then they operate self-controlled via the incorporated hardware and software. For all the systems that we supply, it's an option to install remote control, which then gives access to the units so that the key operating parameters can be read out, and the system can be checked for alarms, for example, or any event messages without having to travel and go there physically. Depending on the type of application, UV systems can look very differently. The two main groups are closed vessels on one hand and open channel systems. Closed vessels are operating under a certain water pressure, mainly in drinking water applications, becoming a part of municipal drinking water supply systems, but also wastewater when it comes to reuse, for example, are pumped through pipelines, and then the closed vessel systems become the most suitable solution. Large streams, especially of wastewater, are running through gravity, under gravity through open channels. So there, a closed vessel would not be the best, most cost-efficient solution. This is where open channel systems come into the game, consisting of lamp modules. On the picture on the right-hand side, you see 3 modules consisting of several lamps that then disinfect the water that runs continuously through the lamp arrays being disinfected. Those types of systems can be used for very different applications. The main fields are drinking water disinfection. This is the classic application of UV, where the use of UV has started historically 100 years ago, treating municipal drinking water supplies. The second field of application is municipal wastewater. We just saw an example of an open channel system. And there the purpose is to treat the effluents even for discharge or for reuse in irrigation, for example, or direct generation of production of drinking water again. A very diverse field for the application of UV is industrial liquids. Those can be used for production of food in the food and beverage industry, for example, in fish hatcheries, pharmaceutical industries, basically any industry that requires pathogen-free water of good quality is a potential user of UV disinfection. With our Wedico branded portfolio by Xylem, we can serve all those applications with specifically designed product series, and we can look back on a track record of more than 150,000 installed systems globally. Having a closer look into one of the 2 classic applications, which is municipal drinking water, UV is not the only treatment. Usually it always is part of a treatment chain consisting of several treatments. At least the filtration step is always required to make sure that solids are separated and that any disinfection can be applied efficiently. For UV, there are international standards that have been developed and are applied that assure that a UV system just not follows the vague ideas of how it should be used, but it is prescribed very specifically how a UV system should be designed, tested, and operated so that safe and efficient disinfection is guaranteed when the design is made according to those standards. DVGW, which stands for the German Association of Drinking Water Supply, and the US Environmental Protection Agency, those are 2 entities that have established internationally recognized standards for safe disinfection of drinking water by UV. The next slide shows an example of a flow chart where surface water is being treated. Very often, UV becomes part of a so-called multi-barrier treatment concept, where not just one treatment, but several treatment steps contribute to the reduction of pathogens that may be contained in the surface water as raw water. Here, for example, separation in sand filtration, ozonization, and the activated carbon filter have a contribution to improving the microbiological quality of the raw water. And UV then is added as one additional specific disinfection step, in this case of surface water, especially targeting at Cryptosporidium and Giardia. As mentioned, those are 2 parasites that have caused huge outbreaks in North America, for example, at the late 90s, with several 100,000 of infected people and several hundreds of deaths. Those parasites are very resistant to chlorine. So those outbreaks have been caused by the parasites contained in raw water traveling through the conventional treatment without UV, and have caused those outbreaks. It has been found out that UV is very efficient in disinfecting Cryptosporidium and Giardia, and that has contributed strongly to the popularity of UV disinfection becoming a part of drinking water disinfection globally. The second most important application of UV is the disinfection of municipal wastewater. One may question why wastewater has to be disinfected, as it still contains organic matter and microorganisms, and it's just discharged to a river or a sea. The reason here for disinfecting, again, is not the absence and potability of the water stream treated. The purpose of treating wastewater is to assure that the microbiological condition of the effluent is adequate and suitable for either discharge into rivers and bathing areas, for example, at this coast, or making sure that the effluent stream can be reused for irrigation purpose, for example, of golf courses, gardens, in the agriculture, or as a service water stream on the treatment plant itself. So again, disinfection here plays the role of adjusting the microbiological quality of the effluent stream to the later purpose of the effluent stream that often, even in very dry areas, is subject to reuse and under different aspects. Also in wastewater, as in drinking water seen before, UV disinfection will usually be the last treatment step to adjust the microbiological quality of the water right before discharge. The second reason for having UV being the last treatment step is that the better the water quality is when it enters the UV unit, the easier the disinfection is, and the more efficient UV light can be used for pathogen reduction. Globally, we operate several thousands of systems for wastewater disinfection, including India, and we are able to design the systems according to very different microbiological discharge standards, from just eliminating a certain concentration down to establishing reuse quality for the production of potable water, for example. The next slide then shows, as an example, the microbiological concentration of coliforms. In this case, it demonstrates that the coliform bacteria contained in the raw water is reduced to a certain level by the conventional treatment, but in order to comply with very or more restrictive discharge standards, a disinfection step is required, which is usually UV disinfection. Looking at chlorine as being still popular alternative process to wastewater disinfection, it can be seen that UV disinfection provides a lot of benefits. The main ones being that UV disinfection just acts on the bacteria, inactivating bacteria, viruses, and parasites, but it does not generate harmful byproducts as chlorination does. It's also non-corrosive. It does not mean an operational risk by handling aggressive substances, and it's very easy to control, and is independent from variations of pH or temperature, for example. With the next slide, we take a look at the Wedeco UV portfolio. In this slide, you see an overview of products that we supply for different purposes. On the left-hand side, the smallest system series named Aquada is for residential and commercial use, mostly disinfecting potable water at the point of entry of hotels, restaurants, or residential areas, for example. And then walking up the flow rate range, ending up with the Spectron and K143 on the right-hand side. These are the standard or mostly used product lines when it comes to municipal drinking water disinfection, up to very high flow rates. The city of Vancouver, for example, in Canada, with 2.5 million inhabitants, the drinking water supply of that city is disinfected by Wedeco UV systems of the K143 type series. In between, there are several product lines serving special needs like salt water, non-corrosive media, or special industrial applications. The next slide then shows us the most used product lines for municipal drinking water supply. On the left-hand side, the Spectron series. You see one system connected to the pipeline and the drinking water works. So from the right-hand side, the water enters through the flange, the reactor flowing through it continuously, being exposed to the UV light emitted by the lamps, and then leaving the reactor through the reactor on the top. This is a continuous process. UV disinfection always works with continuous water flow, and the contact time is very few seconds, so it's a very fast and efficient process. When you look at the left-hand end of the reactor, you see the black connections. These are the lamp connectors from where the cables then are conducted to the electric control panel. On the right-hand side, you see the electrical cabinet with the controller from where the system is controlled and monitored. And again, a remote control is always an option for our systems. On the right-hand side, the K143 product. There the lamps are, we have a different geometry. There the lamps are arranged perpendicular to the flow, so forming a grate where then the water runs through. This is a design very efficient for larger flows of municipal drinking water, and can also be used for reuse and advanced combination with oxidation processes. Both systems, Spectron and K143, they have different types when it comes to a number of lamps, treatment capacities, and can be adapted to different types of waters, and flow rates also by installing several units in parallel or in series. Next slide. This is the portfolio that Wedeco has for wastewater applications. Usually, wastewater streams start at 500 to 1,000 cubic meters and can go up to several 10,000 cubic meters per hour. Here it's important that systems are modular so that they can setups can be arranged, coping with different water qualities, very high flow rates, and also strong flow rate fluctuations. The standard product, which is the most used for wastewater disinfection, is the Duron product, which also as an iDuron is a special version that is manufactured locally in India, especially for the Indian market and the Indian requirements. On the next slide, you see again a little close-up of the Duron product. It consists of lamp modules that are arranged in an angled way in an open channel where then the water runs through continuously. The two versions, the Duron and the iDuron, differ a little bit in the mechanical design, and which makes the iDuron more cost-effective by having one lifting frame that allows to lift out the lamp arrays via a lifting device for maintenance or lamp replacement, for example. And the iDuron is manufactured in India. That is an overview over our main product ranges that are used for our main applications of UV disinfection, which are municipal drinking water and municipal wastewater disinfection. Having a look at the general advantages of UV disinfection, the first point to be mentioned is that UV disinfects very efficiently. It's a pure disinfection effect, so it really concentrates on inactivating the pathogens by destroying the DNA. And it's also very efficient against microorganisms which are resistant to classic chlorination, for example. UV works without chemicals, and that means that there are no side reactions taking place that would create harmful substances like chlorination does. This also makes it very interesting for industrial applications where very pure water qualities are needed without generating undesired substances. Another operational aspect is that no chemicals have to be handled, connecting gas pipelines, exchanging gas bottles, handling hazardous or aggressive liquids. This is all not needed when UV is used as a disinfecting agent. And UV reacts very fast, very quickly. As said, the retention time or the contact time with UV lamps is usually a few seconds. That means there are no needs for excavation works for large contact chambers as known from chlorination tanks, where residence times are 20 minutes, 30 minutes, 40 minutes sometimes. The disinfection takes place where the lamps are, and this is a very fast process, just taking a few seconds, which then requires also very little excavation work for the systems. These are the benefits that UV provides in general. There are certain things that UV does not do. Apart from being a very cost-efficient, very focused, and byproduct-free disinfectant, it does not attack other contaminants or substances in the water. So it does not reduce turbidity. It does not remove iron or manganese. It does not reduce organic substances. It also does not provide a residual effect. So when you look at drinking water disinfection, for example, UV may be the main disinfectant being used in the drinking water works, and then followed by a slight addition of chlorine, for example, to provide the residual disinfection effect during distribution through the municipal pipeworks. This is also where chlorine and UV can be seen as complements when it comes to drinking water, municipal drinking water treatment, and its distribution, so that chlorine is just added at a very low concentration to provide the residual which UV cannot provide. In wastewater, that residue is usually not required as the water goes to a recipient body like a river or the sea. Returning quickly to UV not changing water constitution and not removing turbidity or iron or manganese, or organic substances. This is then where ozone comes into the game and has its specific strength as an oxidizing agent. And so I hand over back again to Tim and Sebastian, who will take you through an introduction to our ozone technology.
Yeah, thanks, Per, and welcome from my side. Namaste. My name is Sebastian Besser, and I will start here with the introduction to ozone in disinfection and oxidation matters. Let's have a short overview of what we will cover here. We will start with what is ozone in general and how does ozone work. We will then have an outlook over some applications, and last but not least, we will have a look over our ozone system portfolio from Wedeco. Ozone was discovered when we're looking at the next slide in 1840 by Mr. Schönbein, and the first ozone generator was around 1850 invented. Ozone is in practice for over 100 years for treatment of different applications, like the first full-scale drinking water installations popped up around 1890s to 1900 in Europe. Today, ozone is widely known and accepted as a proven technology for all kinds of oxidation purposes like disinfecting or decolorization, all treatments where you need a strong oxidizing agent. On the next slide, we will have a brief overview of what is ozone. So ozone is the triatomic form of oxygen. So not just 2 O atoms, but 3 O atoms. And the word ozone comes from the Greek word ozone that just means smell, or to smell. The most important point maybe from ozone is, besides the strong oxidizing potential here, that it has a short half-life, so it cannot be stored or transported, and so it must be generated on site. This is why we are selling ozone generators and not ozone gas bottles. On the next slide, we see how ozone works. Ozone generally attacks all double bonds in molecules, some more or less strong. So it follows 2 pathways in the chemical reaction way. One is a direct ozone reaction with the target compound, and one is the indirect pathway where ozone disintegrates into short-living but stronger oxidizing hydroxyl radicals. Both reactions will always appear simultaneously, so there are some tricks and stuff you can do to steer it in one or the other direction, but in general, everything appears on the same time frame here. Ozone is always compared to chlorine because chlorine is widely used and known for chemical oxidation, but ozone reacts up to 3,000 times faster than chlorine on the bacteria side. So there are a lot of benefits in using ozone for disinfection. On the next slide, we see how this is explained. On a chemical way, we have here described the oxidation potential of different oxidizing agents. And we see that the hydroxyl radical and the ozone molecule itself have the most powerful oxidation potentials way before chlorine or chlorine dioxide. This is why we have these fast reaction times and this high potential of oxidation. On the next slide, we have a basic idea of how an ozone generator from Wedeco looks like. In the upfront here on the right-hand side, we see a medium-sized ozone generator where the power supply unit with the cabinets is located on one skid with the ozone generator. So everything is on one skid and ready to operate at your facility. And on the lower and in the left side of the power slide here, you can see a very big ozone generator, which is oriented in a horizontal manner here, and the power supply unit is on a separate skid. We can operate here up to 1.9 megawatts. So a lot of energy can go into a lot of ozone here. But how does an ozone generator looks from the inside, or how can we describe how an ozone generator works? Basically, we having a shell-to-tube heat exchanger, as you can see here, and in every tube, the ozone electrode is pushed into. And we have on the outside of this shell and tube heat exchanger water flowing to cool the whole process. And the ozone and oxygen gas is pushed through the tubes where the electrodes are sitting. Then we are applying an electrical field or electrical power to the electrodes, and we are splitting with these silent discharge barrier field then the oxygen molecules into atoms, and these atoms are recombining to ozone. This can happen up to 15-16 weight %. So from 100 kilograms of oxygen, you will apply to the ozone generator up to 15 kilograms of ozone will come out of the process. On the next slide, we will have a short overview how the whole process works. So you have three basic needs for the ozone generator. One is the source of oxygen, one of a source of energy, and you need a source of cooling water to cool the process to have it in an efficient operating manner. After the whole process is finished, a mixture of oxygen and ozone gas can be transferred to a reaction chamber, a contact basin, a diffuser system, an injection system, any point of need. In this case, we have a raw water stream where we have fine bubble diffusers that are reacting with the contaminated water, and the treated water can go after a certain reaction time out of the process. On the next slide, you can see how we are defining all these systems. So you need a power supply, which is designed and engineered by Wedeco, and the ozone generator, which is designed and built by Wedeco. You furthermore need an air or oxygen source. You need a cooling system, and you need an ozone destruct to destroy any residual ozone that can be harmful after the process if there's some leftover ozone after your reaction. Next slide. So the advantages of ozone treatment are ozone is one of the strongest oxidizing agents available for treatment purposes. It decomposes after the reaction back into oxygen, so there's no harmful byproducts in the outgoing ozone gas. It's safe to handle because it is always just produced when there is a demand, so there's no storage that needs to be safe or anything. And it can be implemented by an automated process. So it's sensor and data-driven controlled, and security protocols like ambient air monitoring is in operation. Additionally, the whole system can be operated remotely, so no operator has to go to the ozone system. It's all possible to have a remote operation there, and even oxygen can be produced on site by a PSA or VSA system, so no logistics for supplying liquid oxygen in the best case. The next slide will show us here just a small idea of how to tackle an oxidation problem. So how do we get rid of the worm in the apple? So how do we get rid of the contaminant in a complex water matrix? You have two options in the use of ozone. Either using a fine knife and try to get rid of the worm very precisely here. This is by using, in comparison, ozone just as the molecule itself. It's very the double bonds in certain big molecules, and you will have a dedicated breakdown of molecules. Or what I already mentioned occurs simultaneously. You can use the hydroxyl radicals that are formed in the process and just tackle everything that can be oxidized and is very strong but very non-selective. So both pathways will occur in the same time. We have some possibilities to steer it either in the one or the other direction, or it depends on your target component. On the next slide, we will have a showcase here of how ozone is compared to chlorine in the disinfection. So chlorine must diffuse through the cell wall of a bactericide and then inactivates the bacteria. So this takes time, and there is a possibility of, some bacteria can survive this procedure. But you do not have this problem of diffusing into the cell wall and so on. Ozone just destroys the bacteria. So there's no way the bactericide can survive this. And so the disinfections happens in a really fast time frame here, and there's no way for resistance. On the next slide, we can see how ozone can be used, for example, in an industrial way. We can decolorize or break down big molecules like COD or color molecules with a higher dose. So it's all depending on the dose. Using less ozone brings you less effect, more ozone brings you more effect. Comparing it to the, next slide, please. So different different doses are needed, as I mentioned, for the ozone application here. For disinfection, we are talking about 0 to around 5 grams per cubic meter treated. And this can range from 1 to 10 min of contact time. On the other parameters, Tim will tackle in a few moments. Next slide. The key application for treatment of wastewater are COD reduction, color removal, disinfection, reduction of emerging contaminants like endocrines or dioxins. Let's see how these will be implemented in the water work. We have 3 main parts where the ozone can be applied. We have the preliminary treatment, the secondary treatment, and the final treatment step where ozone can be applied. And on the next slide, we will have a short overview of what the benefits are. So in the primary treatment step, we can use ozone to remove toxic substances like phenols, or we can oxidize manganese, iron, and so on to be filtered out afterwards. In the secondary treatment step, we can use it to reduce sludge or reduce sludge. What I missed in the first step here is you can also use it to enhance flocculation and sedimentation. So there are projects where ozone is used to enhance the forming of flocs in the settlement step. And in the final application step here, the ozone in the tertiary treatment, you can remove micropollutants, have an additional disinfection step before going to the water net, and you can use it to remove COD and decolorize your water. Next slide. Now Tim will take over and show you some industrial applications.
Thank you, Sebastian. Let's have a look to the industrial applications for ozone. So you maybe have already noticed that ozone can be active and helpful everywhere where it can fulfill its oxidation potential. And that can be, on one hand, reacting with any substance in water, but it can also react with gases, so gases emerging from some processes, where then it is used for removing the smell or even to detoxify the emissions, like from nitrox oxides. But it can also be used to treat products. So this could be fibers for paper or clay and many other areas in the pharmaceutical industry, for example. If we then go to all the gas utilizing ozone systems, that is a GSO range for smaller applications. And then we enter into the SMO range, which is fully automated ozone systems with process control. And the key differences of those SMO and PDO Evo Plus systems is just the capacity you need. So with the example of the pulp and paper, very often we would be in the range of PDO Evo Plus, for example. Here, as an overview, I have the different systems again with the different features they are offering. Whereas the GSO series is a more primitive ozone system without process control. The other ones have this process control. However, one thing they all have in common is the ozone generation technology. That is an ozone electrode that is very, very effectively producing the ozone, which is safe, and it doesn't need special fuses or cleaning for its operation. Therefore, it is very much maintenance-free. And then there are some differences of the systems, whereas the SMO 100 and GSO series are only CE certified. The SMO Evo Plus and PDO Evo Plus systems provide larger capacities of ozone, and they are CE, UL, and GHOST certificated, which is maybe sometimes important as well with international engineering bits. One thing really to stress, which is special about the ozone products from Wedeco, is the generation principle. And this goes down to the so-called Epheson ozone electrode, which you see here in this picture. And this design is where this splitting of the oxygen is happening that my colleague Sebastian has shown you before. How does it work? We put power on the left-hand power connecting unit, and then the power is distributed along this central glass rod that you see there, which is covered with a mesh. And this mesh is a very stable stainless steel wire that is carrying the power into the electrode arrangement. Then there, this discharge, the plasma, is starting. This is creating then the ozone from the oxygen. And one really special thing that we have is we have one gap at the rim of the glass tube, and we have one gap where the stainless steel tube for the cooling is. This means we have incredibly large surface area where we are converting the oxygen to ozone. And this is making a very, very stable production. Even in a case when a system would have a defect due to, for example, no cooling, the mesh of one electrode affected would just melt and would decouple this element from the power, and would the system would remain in a safe state. So the advantages of this heart of the radical ozone systems, these ozone electrodes, they avoid the need for regular cleaning. They do not need a special fuse for protection of the current. Therefore, it's not adding any artificial costs for maintenance or parts on it. And it's adding to the high availability of the systems. And Radico warrants a 10-year warranty with these electrodes to show and demonstrate the successful and strong design of this core element. And I like to close here on the ozone part. And if you have any questions, please, as pointed out by Dheeraj in the beginning, put it in the chat function, and we are all, that is Per Krüger for the UV part, Sebastian Besser, and myself, happily answering your questions. Thank you.
Yeah, thank you. Thank you for a detailed session. Thank you all the panelists. So now we'll go on to the Q&A session. We can have a few questions one by one. I'll ask my colleague, Mr. Narayan, to help us out to filter it out few questions. Narayan, are you there?
Yes. Good evening, everybody, and thank you so much for your patient listening and trust. The concepts are clear. Pia, Sebastian, and Tim, if you could just go through the Q&A, you will see a thread of questions there in the Q&A section. So you could pick up the ones that are common and answer them as you go ahead. I'll let three of you go ahead and look at the Q&A and answer them.
Okay, thank you. This is Per Krüger. I suggest I just start by picking a few UV-related questions, and then we can take a few, one of the ozone ones. There are many questions in here, so there's a lot of interest for follow-up, and I'm afraid that we may not be able to address all of the questions during this session here, but we'll follow this up in written, so making sure that everybody gets the answers. The first question I would like to take is, do we use the whole wavelength range from 200 to 315 nanometers, or do we use a specific wavelength for UV lamps? And maybe does the wavelength vary whether we are treating wastewater or drinking water? The question here is that there's one principal wavelength, and this is 254 nanometers. The reason for this being the main wavelength is that here the DNA that is the target of the UV rays is absorbing most of the energy. So this is the most efficient wavelength, and most of our lamp technologies, they really focus on that 254 nanometers. Other wavelengths may have a certain contribution to disinfection, but also may have undesired side effects. 254 is the most efficient, and that's the same for both drinking water and wastewater. The next question is, how far does chloride in water affect the materials? That's a very good question. Usually, low chloride concentrations are tolerated by the UV reactor or module materials. The standard stainless steel quality that we're using is 316. At higher chloride levels, we can move to alternative materials like duplex stainless steel qualities, being highly corrosion resistant, or polyethylene materials. These are no obstacles. For example, if you look at fish farming industries or the treatment of reverse osmosis intake water streams, they have higher salt concentrations deriving from seawater, and these are applications where UV systems are very suitable for. Another question is on cost comparison between UV for disinfection and chlorination. First of all, the main driver for UV being used as a disinfectant for wastewater are mostly concerns when it comes to byproducts, harmful substances that are generated by bringing chlorine in contact with organic substances, then forming undesired substances, residuals. On the economical side, it depends on the chlorine cost and the local regulations also. When you do a full cost analysis considering excavation costs, considering chlorine storage costs, when you consider the whole package, also power consumption and lamp replacement, then UV can also be more cost efficient. This is project-specific evaluation to be made, and Xylem is happy to assist you there in in specific cases. I would say then we can. There's another question on UV. What is the reaction time for UV? As mentioned, UV disinfection is a continuous process where the water runs along the lamps without pausing. The contact time of the water in the area where the UV light is produced is usually a few seconds, from 1 second or less in drinking water to several seconds, 3 to 5, when it comes to wastewater or very high doses or very low water qualities. Another question was on drinking water treatment, where chlorination today is mostly used to provide a residual disinfection effect in pipelines. As said, the residual effect is something that UV cannot provide, and this is a point where UV disinfection and chlorine become complementary. They help each other, with UV being able to take over the most portion of the disinfection, especially of pathogens that are resistant to chlorine, like Cryptosporidium parasite, for example. And then chlorination follows by providing, at a very low dose level, a residual effect during distribution in the pipeline. Well, looking at time, I would like to hand over to Sebastian and Tim to take some of the questions related to ozone. If there's time left, I'm happy to go back to some of the UV related questions. Otherwise, we would answer them in written after the presentation.
Okay. There was one question if we would be using either ozone or UV in wastewater treatment. The typical way is looking at the specific treatment targets. So that means UV is very effective in disinfection, and if the water quality from the transmission, how you can apply the UV light to the water is very effective, and then you would go for UV. And if the UV process would be more difficult, we would then utilize ozone. Other reasons to use ozone is as well if there are treatment targets to be achieved that cannot be facilitated with UV. For example, if you want to reduce certain organic molecules and oxidize them, or you want to deactivate and destroy pharmaceutical residues, that would be all indications for going with ozone. So these two technologies complement each other as well in the design. So we are not force feeding anyone using one or the other technology. We are taking on the project specific case the best that is suitable.
Yeah, I have here one question. Sebastian is speaking here where it's referenced to the BOD and the COD. I think this was about the ozone usage. So when we are using ozone, we normally increasing the BOD, so the biological oxygen demand, because we are breaking down bigger molecules that are normally not able to be processed by bacteria. And so we are making more of these molecules biodegradable, so the BOD is increased, and so the ability for traditional water treatment plants on a biological base is enhanced, and the COD is then afterwards removed. So the COD will decrease, the BOD is increased, so we are transferring just chemical degradable oxygen demand into biological degradable oxygen demand. And therefore, we have a lot of cases where we are using ozone before a biological filter to enhance the capacity and the effectiveness of a biological filtration step.
There is another question about how does the cost and operational maintenance of ozone systems differ from RO systems? So a key difference really is the amount of electricity used for the ozone production is lower than in the RO systems, and we are not producing a waste stream of the permeate, and the maintenance requirements from ozone systems are very low. So that means the ozone system itself is very maintenance free, and it is just the upkeep of standard instrumentation, for example, of the oxygen supply to the system, which needs infrequent maintenance action.
So here's one
And,
question.
Tim, there is a question on in refineries, which disinfection method is more effective in your point of view and why? Is that something that you can take now?
I would guess that this is an ozone related question.
I assume so.
Yeah. So I would then hand that over to Tim and Sebastian.
So in refineries, we normally do not see a lot of disinfection with ozone. In refineries, we have more NOx removal or wastewater treatment for specific compounds.
Okay.
So disinfection.
Also,
yep.
I think also maybe certain refineries here provide colonies for their employees. Maybe if I'm assuming the question is related to that, if the disinfection is going to be for the sewage, and the treated sewage is going for non-contact applications like gardening, maybe then UV is a good technology. But if it is going to go for reuse purposes, if they're going to use the ETP water for reuse purposes in a cooling tower, maybe then ozone is maybe a choice. Can we put it that way?
I think that's a valid statement, and that goes in general to both technologies, UV and ozone. The beauty of UV is that it's very selective and has an action purely on the microorganisms, bacteria, viruses, and parasites, and it just inactivates them, and there's no other side effect. The application range of ozone is much broader. Ozone is a very oxidant, and it basically attacks everything which is in the water, and that may be a microorganism, that may be a colorant, that may be other organic or inorganic substances. So if you want to have a broader quality lift of the water, removing several constituents at the same time or degrading several constituents at the same time, then ozone is the choice. If the matter is of specific disinfection, then UV is more efficient.
Yeah, thanks, Pierre, for answering all the questions, relevant questions. So thanks to Tim as well, and thanks to Sebastian. The rest of the questions will be replied separately by us. So we'll take care of all the queries. We have Dr. Nitin Bhate, Senior Marketing Director, Xylem Water Solutions India. So he'll be taking this opportunity to close the session and to thank the speaker. Thank you.
Hi, Dheeraj, can you hear me okay?
Yeah, Nitin, pretty well. Thank you.
Okay. So thanks first of all to all the participants. We had a good attendance, excess of 120. So I think thanks to all the participants for very engaging. We didn't have, we couldn't interact during the webinar, but I could see from the questions and from the chat window that there was a lot of interest and a lot of engagement. So thanks to everyone for very active participation. Thanks to our global product managers, Pierre, Sebastian, and Tim for walking us through these technologies and answering questions. The Xylem team locally, is more than happy to help answer any additional questions. This recording will also be available, and we'll make it available through our channels. So please feel free to contact us for any questions you may have, any discussions on any specific project related questions you may have, and we'll be happy to answer them. We'll be happy to bring in our global experts as required. So thanks again, Dheeraj and Naren and Mahesh for organizing as well. And we look forward to many such interactions in future.
Thanks, Nitin. Thank you so much. So the link, this recording will be available on our website, www.xylem.com/India. And you can share your queries on the mail ID, indiasales@xyleminc.com. I close this session over here. Thank you for all the participants and all the panelists to join the call. Thank you. And please stay safe. Thank you.